This is the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm with the Application Support Group here at EasyPower. And as apparently most of us realize at this point, there's been a new release of the IEEE 1584 arc flash standard as of the end of November 2018. And it incorporates several changes in what we've been used to doing and anticipating when we're doing an arc flash study. And so what we're going to do this morning is walk through the basic steps of how to use EasyPower and implement this new standard. So welcome all, and I appreciate your attendance. And as we are in the habit of doing, I'd like to start with a couple of poll questions to kind of get some feedback from the audience. So if you would please participate and share your perspective on the topic. First is with regard to utilizing the new standard. What is your current position? Let's share those results. It looks like it's pretty evenly split across the horizon. And then the second poll question is, at least based upon your current knowledge of the changes, which change concerns you the most as far as the new model? So it looks like most people have weighed in on this. And so here's how we voted on this topic. So in essence, what we're going to talk about is how the different changes potentially affect the different steps or the different parts of an arc flash study. We'll describe a little bit about data collection, and that's probably the area where there's the most discussion about the subjective conditions of the standard. Then we will describe how the modeling is different and how to implement the newly collected data in EasyPower. And most of the heavy lifting as far as the new model and the high number of calculations that are involved are being done by the software, but it's good to know how to access that information, and we will get into that detail. Really not going to talk about the decision to use or not use it. That's more left up to you. So apologies if anybody was counting on that. All right, first of all, when it comes to data collection, as kind of as alluded to by the poll, there are probably the most significant change is the defining of specific electrode orientations which affect the calculations specifically, and the judgment call that needs to be made during data collection as to whether or not the change or the difference between what's being observed and what's considered standard is necessary and will affect the calculations. So these changes include electrode orientation, the air gap between conductors and any particular bus termination, the enclosure dimensions of panels or switchgear or motor control centers, and then the working distance for any particular procedure that's going to be done. Now all of these, and you'll see as we get into the device library, all of these have typical values as dictated in the standard by the IEEE. And so when we get into drawing the one line, by default, those standard values are available. And you'll see when we get into analyze or building the one line, it's not nearly as onerous as it could be. So basically the same recommendations apply, I think, with these new parameters as applied under the old standard, and that is make sure you do a very methodic process or have a very methodical process when you're doing data collection. What I mean by that is take copious a copious amount of digital images, and when it comes to a enclosure dimension that you may or may not suspect of being non-standard, it makes sense to have some sort of a yardstick or a non-conductive reference point in your image, in the image that you take of that piece of equipment. Now, obviously, if it's the equipment's hot, you very well can't necessarily measure the air gap or even the enclosure dimension safely. So this takes a little bit of forethought, but above everything else, document any assumptions you make, especially if the equipment's energized. And in some regards, that's probably the primary reason for selecting the default values. Likewise, make sure you annotate any potential non-standard conditions or procedures. The bottom line here is the recommendation is to use standard values that are built into the tool unless you have a borderline bus that's maybe just a little bit too high in instant energy, and you want to go back and see how using the presumed non-standard measurements could have an effect. And the tool allows you to do that. So it's worth, I guess, holding that in reserve rather than making that a big part of your model building. That is, detailing all the non-standard stuff that you identified. And one point, and I don't want to hammer on this, but has been removed the low voltage exception from the standard. And in the old days, anything was less than 125 kVA as far as the energy supply in low voltage, less than 240 volts, could be excluded from calculations. That's no longer part of the standard, and I'm not going to cover those details here, but I'm just saying you need to make sure you have some sort of agreement with your client, because that could impact the number of buses that you're having to collect data on. All right, so there's nothing earth-shattering here. Basically, have a methodical procedure and document anything that seems non-standard. And again, calibrate with your data collection team on what standard versus non-standard really is. Then when we get into model building, as I indicated, use the default, the recommendation is to use the default values unless you've noted during data collection that you have a non-standard part. And you'll see when we get into the tools that the bus dialog makes it relatively easy on an individual bus basis with the arc flash hazard tab itself. And you only need to enter non-standard parameters if the equipment has been identified as such. Just as a point of note, and we'll touch on this when we get into the tools, the device library includes all the typical values that are recommended for in 1584, and you can verify these, and these are the values that are brought up when you start to model the bus work. Then when we get into, and so this is what it looks like, the bus dialog box. Probably the biggest change or thing you want to ensure is that you're indicating what type of equipment it is. I've highlighted this area because this is something the ratings, this is an area that frequently people have taken a shortcut on as far as not entering bracing. And this is somewhat a soapbox of mine, because this is a function that the tool does automatically as long as there's a number in here and determining equipment duty. So if you've not entered this value, now this could be a default value that's the same for all equipment if that's what you understand, but the equipment calculation of equipment duty, the tool calculation, won't be accurate if you haven't entered a value in this area. This is not new for the standard. What is new is the definition of working distance, electrode gap, electrode configuration, and enclosure size. And you'll see when we get into the tools, if I leave these all at default, then I will get values here that come from the device library based upon the voltage and the description of the piece of equipment. Then when we get into calculations, any new project, and we're talking EasyPower 10.2, any new project built with EasyPower 10.2 will be set up by default using the new standard, and we'll have this set point, this selection made, and will indicate that it's using integrated method for calculating the instant energy. Any project that was initialized or built prior to the end of December 2018 will still have the IEEE 2002 standard. We'll have a couple more control boxes built into this particular page, and more than likely it will be momentary current that's used for arc flash calculations. Now you'll see is when we get into the tool, you can actually change these, and even in the new 10.2 projects, you can go back and look at what the 2002 calculations would be. And then as we get into calculations, something that is new with the 2018 version or 10.2, EasyPower 10.2, is detailing of the enclosure dimensions and the electrode gap, which has been there. And what has also been there but is now slightly different is the determination of whether we're using reduced arcing current or 100% arcing current. If these columns are dart type, then the tool is using 100% arcing current automatically. If this column value or these column values are magenta, then it's using reduced arcing current, and the difference is determined by the equations, whereas prior to in the 2002 version, we manually selected between 85% and 100%, and it was only applied below 1000 volts. This is applied all the way from the full scope of the project, of the scope of the standard rather. Okay, so let's jump into EasyPower and kind of walk through some of this stuff. So here I have a typical one-line diagram. First of all, I'm going to look at the device library, and I want to show you where these variables are. And again, they're down here under arc flash hazard defaults. And as long as we selected 2018 up here as the standard, then these are the electrode configuration that's available, the dimensions, enclosure unit size for that voltage and that style of enclosure. And then you'll also see there's designations for open air, gap, and now these are adjustable, but again, I don't think you want to make a change if you want to use the basic standard values. So you can refer to those as necessary. As I'm drawing my one-line diagram, and I go in and enter data for instance, this particular main bus, I want to make sure I have designated it both the voltage that's there, which is pretty nominal, or standard practice, but rather than select bus type, select the type of equipment that we're actually using, because that will make a difference now on our dimensions. And so when I go to the arc flash hazard tab, I can see that all these are set by default from that device library, and you can see grayed out basically are what those dimensions are coming from the library. If I want to, or if I recognize that there's a different value in that piece of equipment, I might put in a user specified value, and let's say this air gap or electrode gap was measured as 25 millimeter. I would put that in as user specified, separate from the default. So it's pretty straightforward. Again, the recommendation is to use the defaults as a launching off period, and then go back and re-examine any specific bus that may be on the borderline of having instant energy that's excessively high, and verify that it has standard dimensions or parameters, because these will. So to that point, the default from the library for enclosure size is 20 by 20 by 20 for 480 volts. This is the worst case dimension size, but it's not necessarily standard in every 480 volt cubicle, and so it may be useful, because as I put more actual dimensions in here, it will reduce the factor that this has upon the calculations of instant energy. Okay. I think that's probably the biggest difference as far as construction of the model and doing data collection. The next changes are going to be in my analysis package. So I'm going to go to Short-Circuit Focus, and under my short-circuit options, as I mentioned earlier, if I've built the new project from scratch, it will be set up by default as 2018. I can select 2002, and as I do so, it brings back some of the decision points that were available, which may not be available or even necessary in 2018. Likewise, if I've defaulted or set up a new project in 2018, I want to make sure that the calculation method is integrated. Now, just a word of note here. Normally, according to the 2002 standard, we used momentary current because that was recognized as the worst case fault current that would be seen, because it's calculated during the first half cycle of the fault. However, if we have an extended trip time that lasts multi-cycles, that having this designation would actually give us an elevated instant energy calculation, because the momentary current was used for to integrate over the full time of the trip unit, the last unit to trip. Whereas with 2018, it's recognized that some longer trip times may see decreasing arcing fault current, decreasing bolted fault current as well. And this can be accommodated, because if I've selected integrated method, the current used for the first cycle is half cycle current. If the fault lasts longer than a cycle, then for the next 8 cycles, the tool uses the interrupting current, or the 5 cycle current. And if the fault lasts longer than 8 cycles, then the tool uses the standard, or what we call 30 cycle current as far as that integration. So you actually get a more realistic value of instant energy, because it uses the more realistic current for each trip time or tripping device. Likewise, and you'll notice we don't have a selection between the 85% and 100% arcing current. That's handled automatically. So once we've made these setup changes, we're ready to go into our faulting all of our buses, and we look at instant energy, we'll look at the instant energy calculations. And what I recommend, again, is going to the Arrange for Arc Flash display. And what we see here, there's a number of new columns that include the dimensions of the enclosure, and we can see where the dimensions are standard versus non-standard, and these can reflect customized data entry, or different voltages. Likewise, where we have magenta type in these columns, the tool is automatically using reduced arcing current for instant energy calculation. And again, this is an automatic feature. It's not something we have control over. It's just an indication that that reduced current is being used. Where it's a dark type, the tool is using 100% arcing current because that's producing the most conservative result. And again, this is applied across the whole 15,000 volt range. So the heavy lifting as far as the calculations are being done by the tool. All we have to do is set it up correctly and we're off and running. Now, one point I was going to make is just a point of note. If I have several, or if let's say my whole plant has switch gear that has non-standard dimensions or non-standard electrode gap, I can go into my tools tab up here at the top and set up by default that particular type of equipment such that those new dimensions for either the enclosure size or the device type or the air gap can be saved, and so that I don't necessarily have to change every particular device. So that can be set up under my bus designation, and then as I use the bus as the icon, it will default to the values that I've entered. So that can save me a little bit of time. All right, so the changes are relatively significant, but again, the tool does most of the work as long as the data gets entered correctly or accurately. And at that point, I'm ready to see if we got questions. So the enclosure dimension, the question is the enclosure dimension for the entire switchgear lineup or just for the individual bucket? That's a good question. So it's for that piece of bus. It's bus dependent. If I come in and look at this particular piece of switchgear, and let's say this was a motor control center, and I look at my arc flash hazard tab, my electrode configuration I could have multiple configurations inside of that continuous bus. It could be a vertical in a closed box, vertical terminated in a barrier, and in some elements could be horizontal. So I can literally pick all three and the tool will calculate the worst case value. Likewise, the truest electrode gap. So I think the question that is being asked is, do we have to set it up for individual bucket? The answer is no. You set it up for the whole bus, and consequently you get the most conservative value as a result. So again, the closer it is to 20 by 20 by 20, the more conservative it is. So if you have anything that's greater than that, you're welcome to use it. But even if one bucket only has a dimension that's the smaller size, then that's what you need to use for the whole setup. I think I answered the question. All right, that pretty much covers everything I wanted to talk about. I want to encourage folks to check the website periodically because there's a lot of new information being made available. There is just the announcement now for the Revit integration module and the new reliability module available from EasyPower. As I mentioned, there's additional webinar videos on 1584 changes that give more details comparing before and after to see if there's how much you could expect things to change in your calculations. And by all means, I encourage you to follow EasyPower on social media. Thank you for attending today. Anything we didn't get to question-wise, we'll follow up with an email. Have a good day.